Good morning, everyone. My name is Mhanna, and I'm a research associate at the American University of Sharjah. Today, I will be presenting our paper, Effect of Flange Geometry on the Shear Capacity of Reinforced Concrete T-Beams. The co-authors of the study were Professor Rami Hawileh, myself, and Professor Jamal Abdalla. This is the outline of the presentation. I will start with the introduction, followed by giving the research significance. Then I will explain the design models used and the experimental database used to assess the design models. Following that, I will be explaining the results and discussing them, and I will finally conclude. The nominal shear capacity of reinforced concrete beams usually comes from the superposition of concrete and steel reinforcement. The shear capacity of concrete comes from three parts. The first one is the shear resisted by the concrete in the uncracked compression zone. The second one is the shear transfer by the aggregate interlocking at the edge of the diagonal shear crack. And the last one is the double action from the longitudinal reinforcement. The shear capacity of the steel comes from the internal steel stirrups. Due to its complexity, study on shear has been extensively carried out in the last decades. Most studies in this area have focused only on reinforced concrete beams with rectangular cross-sections, but not T or L sections. The available literature focused on main parameters that affect the shear capacity, such as the concrete compressive strength, longitudinal reinforcement ratio, shear span to depth ratio, effective member size. However, very few studies investigated the effect of the size of T sections and the flange contribution to shear capacity. Reinforced concrete T-beams are being used for diverse application in the construction industry. When the slabs and the beams are cast monolithically, a portion of the slab acts integrally with the beam and bends along with the beam under loads. This phenomenon is seen in the beam-supported slab system, as you can see here in this figure. Such examples include bridge decks, building floors or slabs, retaining walls, and parking garages. Current design guidelines do not include the contribution of the flange to shear capacity in their design models. The shear is only assumed to be carried out by the web of the cross-sections. Recently, several studies have proved that the influence of flanges is not negligible. First, a study by Ramadan et al., they showed that the enhancements in shear capacity of the T-section compared to the rectangular cross-section was 27 to 54%. In addition, increasing the width of the flange had less effect than increasing its thickness. In another study by Tamrin et al., they tested 3 T-beams and their corresponding 3 rectangular beams in shear. The results indicated an increase in shear capacity of T-beams by 5 to 20% compared to the rectangular beams, depending on the longitudinal reinforcement ratio. Finally, Ayanza et al. Developed 3D finite element models to quantify the contribution of flanges, where they found out that the maximum contribution could reach up to 31%. And Ayanza et al. Drew this graph where you can see even as the geometry of the flange increases, the enhancement in the shear capacity increases up to a certain point, which was found to be by 25%. Research significance. The available shear strength design models predict the shear strength of the beams by considering the web only. The contribution of the flanges is usually not taken into account, despite that it was proven by several studies that the shear capacity of T-beams is usually higher than the equivalent rectangular cross-sections. Ignoring such a contribution results in a very conservative and uneconomical design. Therefore, the aim of this study is to evaluate and compare the shear capacity of RCT beams using shear strength models available in the design guidelines and the literature. In addition, the effect of the geometry of the flanges, such as the width and the thickness, was assessed and compared with the current design standards. Moving on to the design models. The shear capacity of any section is calculated by the superposition of concrete and steel contribution to shear capacity. In 2019, the shear calculations of the ACI were changed to add the effect of the member size and the longitudinal reinforcement. The shear capacity could be calculated by equations 1 to 3 if the minimum transverse reinforcement is provided. However, if it's not provided, the size effect is considered, and we use equation 3 to calculate the shear capacity. The CSA, which is the Canadian code equation, is similar to the ACI. However, it includes 2 extra factors, which is beta, that accounts for the shear resistance of the concrete, and angle theta, which is the inclination of the shear crack. The equations of the British code 8110 and the Euro code are shown in this table. Moving on to the literature shear design models of the T-sections. The first one is by the Zararis et al., which is based upon determining an effective depth, B effective, in such a manner that the depth of the neutral axis is first calculated by quadratic equations and then by the equation of forces, and taken into account the distribution of strains over the vertical sections, the authors derived an equation to find the B effective. Plugging it into this equation, we can calculate the shear capacity of the section. Ramadan et al. Developed an equation based on the simplified ACI method in equation 1. Where the authors modified the equation to include L prime, which is the left or right pultruded part of the flange. The equation proposed by Ramadan et al. Is shown here. Thamreen developed an equation for T-sections without stirrups, considering the width and thickness of the flange that are the main variables predicting the additional shear strength contributed by the flange. The authors gathered data from the literature and used simple statistical procedure to produce an equation for alpha that includes the flange geometry parameter. And finally, the shear capacity of the T-section can be calculated by the equation shown here in the table. Experimental database. A total of 21 T-beam specimens were assessed in this study. 9 specimens did not include any stirrups and 12 specimens included steel stirrups. These specimens were taken from 4 studies in the literature: Thamreen et al., Ramadan et al., Ayenza et al., and Samad et al. The range of the parameters can be seen here from this table. Results and discussion. The shear capacity of all the specimens was predicted using the 9 models that I previously mentioned. The values of the experimental shear capacity to the predicted shear capacity for all the models could be seen in these 2 graphs, for the beam without shear reinforcement and for the beams with steel stirrups. We can clearly see that all design provisions underestimate the capacity of the T-sections. As you can see, most of the graphs that are significantly higher than the unity line, indicating very conservative predictions, especially in the beams with no stirrups, where the V experimental to predicted could reach up to 8 in some specimens. Although Thamreen et al. Predictions were based on T-sections without stirrups, the equation failed to estimate the true capacity of the T-sections, giving very conservative results, as you can see here. For the other equations that were developed for the T-sections, like the Ramadan et al. And the Zararis et al., the predictions provided closer values to the shear capacity of the beams with stirrups and without stirrups, compared to the design guidelines. Moving on, we plotted the experimental shear capacity to the predicted shear capacity for the specimens without stirrups and specimens with stirrups. You can see here that most of the points lie above the unity line, indicating that the predictions were conservative and underestimated, except for a few points in the beams with stirrups that were predicted by Zararis and mainly Ramadan et al. So this table shows a summary of the results and the statistical measures. In general, we can say that all design guidelines were conservative in the shear prediction, where the average ranged from 1.9 to 3.89. The code that provided the most accurate results was the Canadian code, TSA, with standard deviation of 0.7 and coefficient of variation of 36.8%. The ACI equation 3 and the BS8110, the British code, and the Euro code, on the other hand, provided significantly conservative results with the average experimental to predicted values of 3.58, 3.55, and 3.89. Coefficient variation values for these 3 provisions was 62% for all. As for the models that predicted the shear capacity of T-sections, Zararis et al. Provided the most accurate predictions and safe ones for the T-sections overall, with the lowest mean experimental to predicted of 1.42, standard deviation of 0.54, and coefficient variation of 37%. Following that, Ramadan et al. Predictions were also close to the experimental. However, some points were unconservative and unsafe, reaching up to 0.56, as you can see here, as a minimum value. This is because the equations include the shear stirrups in the flange and the web, which substantially increase the predicted values. On the other hand, Thamreen et al. Predictions were very conservative, with the highest experimental to predicted mean of 4.67 and a coefficient variation of 52%. Finally, all the shear capacity values were plotted against the flange thickness to height ratio on the left here and the flange width to the web width ratio, as you can see on the right here. After plotting all the points, a trend line was added to show the trend of the plotted points. As you can see, experimentally, as the flange thickness to the height increases, the shear capacity also increases. All design provisions fail to capture the trend. Most of the predicted points indicate a reduction in shear value as the ratios of HF and to H increases. One explanation could be that the design guidelines do not include HF in its equations, and therefore the predicted capacity was solely based on height of the member. On the right hand, we can see from the experimental line that also as the ratio of the flange width to the web width increases, the shear capacity also increases. The only equation that was close to the experimental line was by Ramadan et al., as its equations include the effect of the size of the flange and the shear reinforcement in the flange. It is recommended, therefore, that more research needed to be done to investigate different flange geometries with different flange and web reinforcement ratios to come up with more accurate models to predict the shear capacity of T-beams and provide economical design for the T-sections. In conclusion, the accuracy of 4 design guidelines, the American ACI code, Canadian CSA code, British BS code, and the Euro code, and 3 models from the literature by Zararis, Ramadan, and Tamrin for evaluating the shear capacity of reinforced concrete T-sections was assessed with the help of experimental database, and the following conclusions were drawn. All current design guidelines tend to underestimate the shear capacity of reinforced concrete T-beams, as the models do not account for the flange contribution to shear capacity. With respect to the design guidelines, the maximum average experimental to predicted ratio, which was the most conservative, was the Euro code, and the least conservative but accurate predictions was the Canadian CSA code. As for the models in the literature, Zararis et al. Provided safe and accurate prediction, while Tamrin et al. Provided very conservative predictions. The design code significantly tended to underestimate the capacity of the T-beams without stirrups compared to the beams that had stirrups. These are the references that we used. Thank you for listening. If you have any questions, please feel free to ask.